Thank you very much. Very happy to be here. Thank you for being in this morning session. So, as I mentioned yesterday, when we introduced Thomas, the notion of tutorial is very vague, and each has its own interpretation. I try to fit it a bit in the themes of this week, but I failed miserably. I wouldn't say miserably, but my approach is more in the classical setting of geometry of Banach manifolds. Of course, there is one connection because we will be discussing a bit about the index and a bit of more theory, if you want, in the Sato-Grassmannian, which is, as you know, been discussed several times during these talks related to the KDB equations. So just a quick reminder of or presentation of notations. You have your complex Hilbert space. It will be infinite dimensional in all the talk. Let's say sim will denote the self-adjoint operators. We pick one self-adjoint projection. And usually U will be the group of unitary operators, but since we're interested in some restricted Grassmannians, it will be a subset of it. Certain precise ways that we will mention in a few minutes. So this usually comes from some operator space or operator ideal I, which is a Banach space inside usually compact operators. And the Banach Lie algebra of U will be, of course, then just a skew adjoint part of this idea. So to fix notation, this is E0 will be the connected component, or one connected component, which means the coadjoint orbit of the.
Probably that means it's a Banach Lie subgroup, right? It's just a subgroup which is Banach Lie group.
Yeah, I meant my original phrasing was Banach Lie group, which is correct. But then the word sub was added because I remember that I wanted to treat special cases. So it's usually not an embedded group. I mean, it's not an embedded subgroup of the full unitary. So the main topics of this short talk is first discuss the linear connection in the Grassmannian, and this is related with my original idea for the talk, which was a kind of presentation of these objects more geometrically. Then quickly see the geodesics and exponential map. In this case, the system, the geodesic flow is really simple and it can be really obtained explicitly, so there's no problems of, say, integrability or such. But we're interested in going a bit passing that point, and we study tangent conjugate points along geodesics. So, as Ali told us yesterday, I think it was, these points are where the differential of the exponential map of this connection fails to be invertible. And there are two kinds in the infinitely dimensional setting of these points, where it can have a kernel. These are monoconjugate points, or it can be non-surjective. Those are called epiconjugate points. And just now a kind of vague assertion, which was our idea when we began working with these topics in our group, follows some kind of a picture like this. If you have your manifold, M, and you have a geodesic, gamma, and you pick E, a gamma of 0, and you pick U, which is, of course, gamma of t, for some t, capital T, which in the notation of connections can be expressed as the exponential from the point P of t for some vector U, B will be tangent to the manifold M. And what interested to Milner was studying the space of paths joining given endpoints. I mean, all the paths, not only the local variations. And this is called the loop space of the manifold. There's some regularity conditions, for instance, in cases it has that both gamma and its derivative are square integrable in some chart, and then in any chart. So these are kind of Sobolev paths, not all paths, but only Sobolev paths. And what's interesting about this space is that the homotopy type of this loop space only depends on the topology of the manifold and not of the chosen points. So the election of points is quite arbitrary. And what is really relevant for the study of the geometry of this space path is that at least in the finite dimensional setting, you can describe it if you know the conjugate points of the exponential map. Because one of the fundamental theorems in Morse theory is that this will have a structure of the CW complex with cells that can be computed as follows. For each conjugate point of order d, order is the size of the nullity, kernel of exponential, there will be one cell attached of this dimension to the CW complex. So you see it's a very precise description of the topology of this loop space. Well, all this was in finite dimension, and our idea was trying to see if we can say something about this for Banach manifolds, for the loop group, where now M is a Banach manifold. So the first attempts were obviously at kind of known examples, and one of the most popular and easy to deal with, at least from this point of view, is the Grassmann manifold. That's why we are focusing on this as an example to our general ambitious and probably unreachable objective. So we now go through these quick definitions. You have this decomposition with respect to the fixed projection in blocks, as Thomas and other people mentioned. It gives you some kind of block matrix decomposition of any operator. And any operator space can be decomposed as the sum of two parts, which are the diagonal and the codiagonal part, always with respect to the base point P. Some names. D is the P-diagonal part. As we will see here, this remark here is incorrect. It should be in the next line, because the codiagonal part is in fact where the orbit lives. Well, now a quick reminder of some different varieties of these subgroups, which are not Banach-Lie subgroups. First, the congruence subgroups, which are defined as follows: just perturbations of the identity by this operator in the ideal. These aren't so popular because maybe they don't have many applications, as I know, for differential equations, but still interesting. And then the restricted groups, where you consider all those unitary operators that the commutator with epsilon, epsilon is just the symmetry of some polarization of the space. So epsilon is reflecting around this. Maybe it's 1 in H plus and -1 in H minus, or vice versa. And the condition to be there in the group is this one. So some quick remarks. From the observations above, you always have, or from the definitions above, you always have this affine space inclusion of the orbit in some translation of the ideal of the operator space. So if you differentiate, you will end up with something like this, because all these guys are symmetric. But in fact, if you take a look at the computations, the tangent spaces will be codiagonal operators. And this intersection is quite long to write, so we'll write it just CP for brevity. Now, since we have the composition in two parts, diagonal and codiagonal, you can project bounded projection. It's very easy. And this projection, when you have the ideal of Hilbert-Schmidt operators, are exactly the orthogonal projections for this Riemannian metric induced by the trace in the Hilbert-Schmidt operators. So in this case, if the ideal is the Hilbert-Schmidt operators, this would be one presentation of what is called the Sato-Grassmannian, or at least one component of it, also known as Sato-Segal-Wilson, because they were developed independently. And we are dealing here then with the Riemannian metric, one say natural Riemannian metric in this Grassmannian. Anyway, just a quick reminder of how to define a connection. The setting is very simple. You don't need much machinery because everything lives inside a vector space. So the idea is just to differentiate and project. That's a covariant derivative. So you take a field along a path, which is just a family of vectors tangent to the manifold at the point gamma of t, and just take the derivative in the ambient space, which are operators. Everything lives inside the vector space, and then you project. And this is exactly the covariant derivative we're interested in. There are several presentations of it. And in fact, when we have the Hilbert-Schmidt operators, since these are orthogonal projections, this is in fact the Levi-Civita connection. No, this is just not extremely necessary, but you can obtain explicitly the formulas for the vector fields for the geodesics. So if you have some Z here, the trick here is that if you begin with a joint operator and you take the commutator with P, you end up with a self-adjoint operator. So this path is clearly in the unitary orbit because Z is Q adjoint, right? Small z is Q adjoint. And when you differentiate, you will notice that will appear a commutator. So the initial speed it will be the one you are wanting to obtain. So with this formula, the exponential map is fairly simple. It's this one. So as you see in this case, since there are very explicit formulas for the exponential, one could try to understand this structure, the structure of the differential of the exponential map at a certain point. Okay, we have this map here, which is a linear map. There's a bit of notation here, but P is fixed, so it doesn't matter. B is where you exponentiate at the point B, the exponential map, and you obtain a map from one tangent to the other. And this is the map we're trying to study when it's a monomorphism, when it's an epimorphism, etc. And the tangent conjugate locus is defined as the points where this is not an isomorphism. Of course, when you take the vector 0, this is the identity, the exponential of at 0 is the identity, so it's an isomorphism, so you have to get away from P to obtain this degeneracy. And the first conjugate point is a smaller b in the tangent conjugate locus of P. You have to be more precise because you have to define some way to measure vectors. And since these are operators, there are several ways to do it because you can use the norm of the ideal, of the spectral norm, etc. But as we will see, what rules here, every ideal is the spectral norm, the size of the eigenvalues. And just a comment, the cat locus, which we will not be discussing here much because I won't be entering into the metric part of the discussion, is a set of points of, in Q, in the Grassmannian, that geodesics from P to Q are not minimizing past Q. Standard notation. And with these two definitions, a quick reminder that in the Riemannian setting, a point is in the cat locus if, well, you have a conjugate point there, or you have more than one short geodesic joining P and Q. And both things can happen. Well, anyway, for our purpose, we have these formulas for the exponential map that I wouldn't say easy to obtain, but you require some manipulation after differentiating, etc., using Lie algebra operations. And there's an auxiliary function that will appear. This is the cardinal hyperbolic sign, just hyperbolic sign divided by lambda. This map is invertible, and this one is also invertible. It's maybe not so apparent, but since Z is codiagonal, then if you apply P again, the commutator, you get back to Z. So ejection, which is between skew-adjoint and self-adjoint operators. So if you take a look at this formula here, this part outside is irrelevant. This part in P is irrelevant. What is relevant is this term here. Everything else is invertible. So we have this self-map, and you can factor any entire function of finite order using Weierstrass factorization theorem, and then apply functional calculus to get this neat formula for the differential of the exponential map, at least the relevant part of it. So add here, it's as usual, the commutator of these two operators. So it's an operator on operators. Now, if we go back to the definition, you have to check when this is not invertible. We have the two kinds of problems, monoconjugate points and epiconjugate points. And this is some joint work with Andrew Chow and Recht. We assume a normalization here. The norm is the spectral norm. So V has eigenvalues or singular values less or equal than 1. And in fact, it has 1 should be an eigenvalue because V is compact. And then you can characterize which T's there should be a possibility to have a conjugate point, and the formula is this one. With these indexes, where K is an integer different to 0, and S and S prime are elements in the spectrum of V, which is in fact symmetric around 0. This is because V is codiagonal. You can prove this by hand. So you have a balanced spectrum, symmetric, and you take any pair of eigenvalues or spectral points, and if there is a conjugate point, this should happen. So in the classical setting, this describes completely the situation because, in fact, all the points of this form will be conjugate. And this follows from some ideas from Crittenden in the 60s. That studied this kind of problem of the order of degeneracy of the exponential map using techniques involving the well chambers and some pretty, I would say, interesting but not accessible for us Lie algebra theory, because we don't have root systems here. This is all infinite dimensional, right? But in the case of finite dimensional Lie algebras, you have all these tools at hand, root systems, well chambers, etc. And the classification was done with this. So we wanted to find another way. So the first conjugate point is when T is smaller, and this should be when the denominator is bigger, and this happens at T equal E over 2. And then this is the first conjugate point, like a half a sphere. No? The picture of the Grassmannian can be sometimes resembled as a projective space, where you have half a sphere, but you also have to identify the equator. So you see that the radius is pi halved, not pi, because it's this identification of the equator. Well, if you make a polar decomposition of the velocity v, you can write with using some functional calculus again, U as a sum of two partial isometries from the range of P orthogonal to the range of P. And the first theorem is the exact set of first conjugate locus is the solution set of this equation. I mean, you have to solve this, and then you have to move it back to the correct space. There's some isomorphism here to do computations, which is this operation. But in fact, you have to try to solve this problem, which is remarkably like an eigenvector or eigenvalue problem, but these are operators. So it would be much harder. Maybe they don't have eigenvalues, or maybe they don't have eigenvectors. That's why these points can fail to be conjugate in the infinite dimensional setting, because in the absence of an eigenvector, there won't be nullity. But the fact is, at the first conjugate point, you can prove that this, if it's not monoconjugated, it certainly will be epiconjugate. So the first conjugate point is always a true conjugate point. Now, this is just a review of more results. You can have a very complicated formulas regarding when these are and when these are not conjugated in other conjugate points past the first conjugate point. For instance, the points of default are always conjugate. And you have if you get back to the full algebra, where things can be diffuse. Diffuse in the sense of von Neumann algebras means that there are no atoms, so everything is kind of a measure space with no discrete measures. You have these problems of scarcity of eigenvalues or eigenvectors. So you can construct examples of where you have a monoconjugate point which is not epiconjugate, the other way around, and you can have points which are neither of those. The situation is much more technical in the diffuse case. But for projective spaces, you obtain a very nice description, which also can be seen as the orbit of a rank 1 projection. So what I really wanted to mention was this last slide, just the point of the short talk. If you get back to the Sato-Grassmannian, you can count dimensions. And since everything is compact, there really are monoconjugate points everywhere. So take a vector and normalize it. So the spectrum is between 1 and -1. Remember that B is Q adjoint. So eigenvalues as single values just differ from a modulus. You don't have to rotate them. And take a geodesic with initial speed B, starting at B, and count the dimension of the fixed point set of B squared. Say, how many vectors fulfill this equation? As you see, since V is compact and Q adjoint, B squared is, well, not positive, but negative, and compact also. And these always have a norming eigenvectors, have a lot of eigenvectors. So the space is not empty, so that's why D is always, this dimension is always 1 or more. And the theorem says that in this case, D is always finite. This is consequence of this finite dimension of the eigenspaces for a compact operator when the value is not 0. And the nullity of the order of the size of the kernel at the first conjugate point is exactly D squared. Where is this D squared coming? Because you have a D by D skewed matrix, and you can count the real dimension, and it's D squared, just like that. And just to finish, you can really exhibit these objects in the nullity of the differential exponential map with some presentation using the eigenvectors for different values of S. You have eigenvectors for S and S prime, eigenvectors for B squared or for the modulus B, which is the same, and you get this very simple elementary operator. Well, after rotation, this will belong to the kernel, and it can be shown that all of them are of this form. You have a complete picture of the nullity. Yeah. So I cannot say much about this because we still have a lacking of good definitions, but we have the orders, we have the index, and it would be nice to be able to say something about the structure of the loop space using these numbers, to count something there. There's many pitfalls in the classical approach because, well, you know, it requires compactness for construction of the CW complexes, etc., etc. That was the idea. And we are kind of confident that these kind of ideas can also work in different manifolds. Just make a spectral analysis of the differential and exponential map to understand the nullity or the index. So it's pretty short list of references because if I try to mention everybody that worked in this would be eternal, but just, well, have a preprint there. Then this is the old paper by Crittenden. he developed a kind of a general criteria from finite dimensional symmetric spaces, and then using this, Sakai, 10 years later or 15 years later, used this to obtain this classification of the index in compact symmetric spaces, in particular in the Grassmannians, the finite dimensional Grassmannians, both the real and the complex case. So the first, I would say, one of the first ideas I've seen about infinite dimensional Grassmannians is here. It is done in the setting of Banach operators. So it's not a Grassmannian in our sense because they are only idempotent elements. They have no notion of self-adjointness. And here is kind of the Riemannian perspective of the Grassmannian in this work by Wong. And you can see how the eigenvalues fit to form this Riemannian metric or a classical approach to the subject.